Hello everyone, it's April 17th. Alright, I'm gonna go right into the problem today, which is an easy one. So that's a good news because I have to handle the problem from yesterday's contest. The last one didn't have much chance to think about because the question number 3 took a really long time, and finally solved problem number 3 using complex number. But I do hope that there could be a better solution. I'll look into this maybe in the next few days, but for now, what's most important is the longest path with with that thing that the last problem. I'll look into it. I have some thoughts last night. I just think it over. But does that really work? I don't know. But anyway, let's go for this one first. Increasing order search tree. Given the root of a binary search tree. Oh, it's binary search tree again. Rearrange the tree in order so that the leftmost node in the tree is now the root of the tree, and every node has no left child and only one right child. So we turn this into this giant thing. So isn't that we just sort them in order? What's the order? Left, root, right, right? Left, root, right, root, right. So all we need is, as we visit them, we're going to connect them together. How do we connect them together? So we can, technically speaking, just get the entire array and then turn the array into a tree, but it would be interesting if we can do it directly while traversing. So we can go left, 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 left. Then what? That shall be the root. Is we go all the way to the left, right? So we go left, 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 and then we find the first one, and then what? And then we say we go right, and then I need to return. Is that requirement like O1 time complexity? I don't know. What would be the better solution without sending them into an array? Okay, create a new node. Okay, and then what? We can create a dummy. We can say dummy.write equals this. Okay, and return. And move the node forward. And then the next one, yeah, we can do that. That's, I don't think that counts as finding a new array, but it definitely works. So here's the idea. I need some global variable. Oh, hold on. Let's just do it here. And the self.dummy, right, equals, let's say, tree node. Doesn't really matter. And then self.node equals self.dummy. Alright? And then def helper node optional. I just go tree node, that's fine. And we don't return anything. Okay? Say if node, right? Then self.node.next equals, let's create a new node, right? Node.val, right? So create, oh no, that's a node next self.right equals this. All right. Now we have to call helper node.left, this, and helper node.right. Oh, and self.node equals self.node.right. We move on. All right. And once we're done, we call helper on the root, and then return self.dummy dot right. That shall do. I mean, is this like a cheating version of? I don't think so. I could have just created the array, but this one saves the array. I don't have to do the array. It saves the memory. Let's see if it's right. Yeah, I think it's right. Oh, my goodness. Oh, so many different methods I used the last time. All right, so that one is done. Nothing too fancy. $8.97. Use a global, it's actually considered a global variable within the function to record the current position of the new link, a new tree. This avoids the need to create a sorted array first. All right, solutions, take a look. What the solutions say? Taking on a traversal. Oh, traversal with relinking. See, that is something I don't want to keep thinking, but I guess this is more real, right? Yield. That's actually a good idea. Nice, good use of yield. Awesome. Using yield. Then I can use that as an iterator. Right? Get each one, push it in. Nice. Nice. Good use of yield. Alright. Traversal with relinking. So I guess it just how do we relink? Okay. Let's think about it. Right? So what happens is the root has to be the left subtree of the left node. And the right, the right doesn't change. Let's go back. So all we need to do is this to 2, 2 to 3, right? And 3 to the right, this one to the right to 5. So how do we handle this? So we go all the way to the left, and then we can record it, and then when we go back here, we just say this dot left, this dot left dot right equals this. No, this dot left, keep going all the way. Right? So the left subtree and all the way to the right will equal to this. Okay. And then we go to its right, which is correct, right? Which is actually not correct, because if I have something here, right, like here, I have to go all the way to the left. So we go to the right, and we need to go to all the way to the left, and then connect these two. You know what? I don't know. How do you do the relinking? It's so simple. Hold on. That's it. We in order. So go all the way, and then node dot left equals none. So we cancel out that. Oh, this is exactly the same as this one. What the hell? What the hell? This is exactly the same as this one. I thought they were relinking inside. Oh, it is. It is. It's cutting the node. You're not creating a new one. Okay, my bad. I didn't see that one. It's cutting. So, you can do that. Yeah, you can do that. That's all right. Yeah, that's not a trick. Ah, I see what it means. Okay, that makes sense. It is a. So yeah, it depends on order of. Wait, what is the order? We assign. I think it's assigned from right to left. So assign node to current. No, current dot right equals this equal. Actually, I don't know. Are they still doing it? Yeah, and then is current dot right equals current and equals. don't write code like this. Give me headache as well. All right, so back to this one. Oh, I need to go to discussion. Actually, no, not discussion. I need to go to problems. I haven't seen like the contest result. Maybe I should see the contest result. I'm interested. Oh, wild card matching. This is a very difficult problem. I probably cannot even do it right now. It's very tough. All right. Oh, we have some other problems to deal with. All right, so this is the one that I didn't solve. This one is pretty hard. All right, let's see. Contest. Maybe I only solved 3, and then it's pretty slow. 3, to be honest. So maybe 1,000 something ranking. Yeah, only got 3, and I have like 2 errors on the third one. Oh, go by 14 minutes. Nice. Huh. 2,000. That's all right. 2,000. It's about, yeah. It's a decent problem. So it took a long time to solve the first one. And I got 2 errors here at 10 minutes. So 1 hour and 5. 2 incorrect attempt. 2,333. That's fine. Okay, so I have an idea of using topological sort. So okay, the question is to see what is the path that contains no adjacent node that have the same value. So definitely we can build a tree, not a tree. Don't think of it as a tree. It's a graph. We'll build a graph out of this, right? And after we build a graph, I want to do topological sort. So we're starting with a one that has only one link, right? We're starting one with one link. And because there's one link, there's no confusion of where things lead to. So they will just go, right? So for this one will go to here, this will go to here, and this will go to here. That's the starting point. So when we cut off, right, and we see on this one, if these two are different, then we report the length at this spot currently is length of 2. And here is the same. Actually, should we include this spot? No. When we go to the next one, we include this spot. It should be like the length up to this spot, not including, so this one will be 1, right? And this will be 1, and this will be 1, okay? And then we check. So these two are not the same. So I can continue and say 1 plus 1 becomes 2. So starting from here, we have 2. And this one is 1. Now here we have issue. We have to compare. So we have 1 arriving here and this one arriving here. But know that these two are the same, right? So I cannot do this, and try to connect to another thing. So we have to restart. So whenever this is the same, we put this 1 into the result, just update the result. And we just don't consider this anymore. And these two are not the same, so 1 comes here, right? And now plus 1, it becomes 2. So now we're starting here with 2. We start from here, it's also 2. And now they go to the next one, right? Next one. So when they go to the next one, these are the same. So 2 go to the result to update. And this 2 comes here, it's not the same. So come here, this will be 3, right? And then this is the last one. So the answer is 3. Now there will be a situation where we have multiples. You see this? Multiples are arriving at this. And this will start from these as well. So we have, this is 1, 1, and this doesn't consider because A and A is the same. So 1 goes to the result. So now we have 2 arriving here, both are 1s. Now we can have a choice, right? So the choice is always, because we have some chain coming here, some chain coming here, and they're all valid. That means we can always connect these chains. So when you define, this will be like an array of chains. You think about there are a lot of income into this node. So all of them has values. So we define the 2 largest values among them, add them together, and we can form that's a path. That's the longest path. So for this case, we have 1 and 1. Well, only 2. So we say 1, right, plus 1, and plus this one, right? So we have 3. 3 is the current. And after that, we find the longest one, combine it, so that's 2, and we keep going. But we don't have any more to go, so that's 2, also upload. So now we have 2, but overall it should be 3. So I want to try this, but I need to see topological sort because I forgot. Like I know the general idea, but I forgot how the implementation. Geek for geek. Alright, let's go geek for geek. Geeks for geeks. God. Alright, so it's for a DAG. This is not a DAG, but it's fine. The idea stays the same, right? The idea stays the same. So vertices? Okay. So we go for, this is the node with all of its neighbors. If it's not being visited, then that's not what I remember. Nah, that's different from what I remember. Hold on. Can I see another topological sort? That was not how I remember it. Okay, well, find a linear order of orders such that for all edges, it precedes W in the ordering. It doesn't matter how there are many ways to perform the sort. This one, so this topological sort. So the one I'm thinking about is, it's not called topological sort then. Is that pruning? Is that called pruning? Graph? Pruning sort? I don't know. I don't know the name. I don't remember. Because I remember is we go from the one with the least number of edges, and then after that we go to their neighbor, right? And then we say among the neighbors. Oh yeah, hold on. Maybe I can just write it myself. That doesn't care if it's a topological sort or not. So we create the adjacency list. Okay, so we create the adjacency list. We have, oh, hold on, adjacency list, and these are the indices. Okay, so we create the adjacency list, and then as we create, we find the ones that has only one neighbor. Okay, so those ones get put out. We can call them a queue, right? And then for each one coming out, we will go to its neighbors. Right? We'll go to its neighbors. Okay. And then once we go to its neighbors, then what? We need to save something in the neighbor, right? So what do we save in the neighbor? We save, hold on, let me think. So I know I'm current node, right? And I'll go to my neighbor. I know if my letter is the same as the neighbor. If it's the same, then I don't save anything in the neighbor. If it's the same, I just update the result. If they're not the same, I save myself in the neighbor, which could be an array. okay? And then, right, and then, oh, how big is the entire thing? Jeez, 10 to the 5th. Okay, and then what? I have the neighbor. Do I put the neighbor in a queue? And basically I need to remove the I need to cut it off, right? I need to cut it off. How do I cut it off? I can put that in a set. So the neighbor I can just, do that and check. Yeah, I check. So every time I push the node out, I find its neighbor, right? And then we do something, like we either push the current length into it or we don't, and then we cut it off from the neighbor's adjacency list, right? So we cut it off. That's fine. And then we count. We count how many neighbors does it have, right? We count how many neighbors does it have. And if it has only one neighbor, yeah, it won't have a one. Hold on, let me think. Will it have one neighbor? That'll be fine. That means just that one doesn't have any neighbor. That one just is a zero neighbor. Okay, if it's a zero neighbor, we'll push into the queue as well. And then we go for the next one, right? And if it has only one neighbor, we should put it into the queue. Okay, if it has one neighbor, we put it into the queue. But then what if the next one also ending up there? If the next one also ending up there, then we have, yeah, that's fine. If the next one also end up there, now we push it again into the queue. This is fine because we only push into the queue if it has one neighbor left, or it doesn't have any neighbor. So if I have one left, I push in it. If it doesn't have one left, we'll leave it out. And then the hope is, because it's all connected, so someone will lead to it. And once it's one, then we push it in, right? And then when we pop out, every node pop out, and we check its array, right? We check its array, and then we do some. Let's try. This is an idea, right? If it doesn't work, there's always. If it doesn't work, there is always hints. I can always check the hints. Okay, so this is. All right. There's a few things, right? There's a few things. So first of all, we need to create the adjacency list. What the hell is this problem? Oh, I remember this problem. Oh my god, that's a very tough problem. All right, adjacency list. How do we do adjacency list? So we have parent. Adjacency list. Okay, so this one will equal to, I don't know, it should be this, right, for this in range len parent, right? And now we say doesn't matter. So the first one is always -1. So we go from the second one, right? So we say for I in range 1 to len parent, okay? Then parent I is the parent of this one. But it doesn't really matter parent, it just means these two has connection. So we can just say AB equals I and parent I. Then we just do adjacency A dot set. Because I need to remove B and adjacency B dot add A. Doesn't matter. We go through the entire thing. Now we have the adjacency list. How do we know where to start? That's a good question. How do we know? Oh, we know because they say this is a tree, right? This is a tree. So they set it out as a tree, which means these are the last few things. So like the last few will always be okay, so this one, it has this. And I have to go through this one more time to check for where do we start. Can we afford that? That's already ON. We have to do another ON to find. We can go from the remaining, right? This. If none of these are mentioned, like this one, none of them mention it, right? So we check for this. If nobody mentioned this. I can say yeah, let's just say Q. Okay. I'm gonna say for I in range. I probably should do n parent. N. Alright, for I in range n, what do we do? If len adjacent I is equal to 1, then we do I don't know, I, just a node, and then 1. We have one value, length is 1 associated to it, and of course result is equal to 0. Okay. So while Q, okay, and temp equals this for node and else lens in Q. Okay. What we need to find, well, we need to see to me, right, the largest two. So we say if it's longer, then we find the largest two, we upload. If it's just 1, right? If it's just 1, that means it just keep going, and we'll handle it at the end, right? We'll handle it at the end. Okay, so now we start from these nodes, right? And then we go to the next node. And hold on, let me think. I should think it should start with 0, right? Start with 0. So I'll upload myself first, right? So say lens.sort, okay? And then we say res equals maximum res and lens this plus 1. That's 1. And then we say if lens is larger or equal to 2, then res equals max res lens minus 1 plus lens minus 2 plus 1, right? So we handle these, right? We handled. Okay, now what? Now what? Well, now I need to find the next one, right? My next. Hold a second. Maybe I can. Why do you even do this way? Right? So if I give you 2, well, I always give you 2. Right? I always give you 2. And I can always do this. Right? I always do this. Which means wait, hold on. You put this inside. We might need another one. Maybe, hold on, nodes. Okay. Then let's just. This is where we store everything. Okay, so this is where we store everything. This is the actual queue. Okay. And then we can do this. I don't have to check anything else. Okay. Once we're done, we say we go for the neighbor. Right. So I only have one. I suppose I only have one neighbor. So we just say neighbor shall equal to adjacency list. Right. Because it only has one. So I say adjacency list node, right? Adjacency is a node, and then turn this into a list, and then grab it. Okay, so that's my neighbor, and we need to check. Ooh, I need need a new thing. I need a new thing. Oh my, I have adjacency list, I have a node. I don't need I. That shall be. Yeah, I just need this. Right? I just need this to record. But the Q, we need to have an I. And we don't call it nodes, we call it lengths. Okay? Call it lengths. And then we'll say node and lengths. Right? We call node and L. Let's call it L. L.sort. Okay. And then rest equals this. And now we have a neighbor. The neighbor, and then if it's the same, and we say if node, S node is equal to S neighbor, so they have the same letter, then don't do anything, right? We just consider that's it. But before we do that, we always should do adjacency neighbor dot remove, right? Dot remove what? Remove the node, right? Okay, so remove the node. Now we check if they're the same. That means we cannot continue. So that's it. We end it right there. And we have to give a new fresh start. Otherwise, if they're not the same, okay? If they're not the same, then we can say lengths, right? Lengths neighbor, right? Lengths neighbor dot append. Append what? Append the current length that is associated. So that shall be L minus 1, which is the largest on that, and then plus 1, and plus the current node, right? So that we go to the neighbors. Go to the neighbor. Okay, so once we've done that, we push it in. Then we say if len, as an adjacency list neighbor, is smaller or equal to 1. Remember, the smaller or equal to 1. Then we say temp dot append. Append what? Neighbor and length neighbor. So this one we can push in. Right? We can push in. Okay. So we might hit it again, but that's fine. Right, that's fine. The topological sort is guaranteed every neighbor is visited once. So we'll do this, and then we put everything, and then we say Q equals temp, right? And eventually, this one will get out, and we say return rest. All right, let's see if this one is right. Feels very makeshift, so I'm not 100% sure. So this shall be 3, and this shall be 3 as well. We have parent s parent s list out of range. All right, how? One step at a time. So we're gonna check. Let's check for 2 things, right? So we first check adjacency list, and then I check for the Q. So adjacency list 0 to 1, 2, 1 have 0, 3, 4, 2 has 0, 5, 3 has 1, 4 has 1, 5 has 2. That's correct. And initially we have 3, 4, 5. That's correct. So we start with right. So now what we're going to do is just check on the queue in the beginning. Alright, so the first queue is right. Second, so after these are gone, we shall push this at 2. 2 is 1. And then 1 should be with 1. Yeah, 1 with 1 as well. Okay. So next one, it shall be 0 with 2 and 0 with, ooh. Now we do need to push it twice. So Q come in, have 0 with 2, and a 0 with 2. And 1, 2 is coming from here, EA. Oh, it should only be... It should only be 1. Why would I have 2? It should be this node is not equal to... Yeah, we have 1. And then 1, the neighbor is 0, right? And then they're not the same, so we got a 2. And the other is 2. 2's neighbor is this, and they're the same. Oh, and they're the same. So only if they are not. Only if they're not. So if they're not the same, right, then we do this. And if len is smaller than, so if we do this, oh, what the heck, that's not right. That's not right. This is not right. This is not right. We have to, hold on, let me think again. If they're not the same, I was just passing mine to the neighbor, right? If they are the same, then we don't pass. Then I can still say if adjacency is smaller than 1, so I push it in. And then this adjacency is smaller than 1, so I push it in. So okay, that's why I got both in, right? I got both in, and the length is updated. See that? The length is updated. So what we can do, we can say if it's visited, right? How do we do that? Well, I can set temp into a set. We can just do a set. A neighbor is not visited. Then we push this one in. If neighbor has been visited, right, then we don't push it in again. So how about we set up another thing called visited, okay? And then for everything, visited, yeah, it's fine. It's fine. It's fine. We'll just say if this and neighbor not in visited, and temp and the visited.add neighbor. Okay. So now we have one of this. That's true. Okay. So now we have 0, and we try to find the next neighbor. Okay, so here is the problem. Now the problem is the neighbor does not have, right? So we say if len adjacency node is equal to 0, then we just continue. Yeah, because it doesn't have a neighbor, so we just say, and now we continue. Okay? How about this one? Alright, so both pass as expected. Alright, let's try our luck. I mean, it is ON. As long as the logic is correct, this one should be right. Logic could be wrong. Oh, we can time out. Ugh. Edge case. Alright, how did you get a 0? Yeah, because the rest start with a 0, and then we start with someone that does not, they don't even go inside, right? They don't even go inside. So minimum value should be 1 because it says n is 1, so at least is 1. So I can do 1, so I basically solve this problem. But then I realized it could be another thing. Let's say, I don't know, -1, 0, right? And it'll be A and A. That should be 1 too. Oh, okay. Actually, I'm not 100% sure, so I'm going to just check this. So let's say as -1, 0, right? A and A. And of course, -1, just A. Oh, so I'll be wrong. Check this one to 1. Try it again. Oh, we pass. We pass. Wow, it's not as difficult as the third one. I don't have to use this trick, but I'm pretty sure the solution does not look like this. I am very, how should I say it? I mean, there's one thing that's really bugged me these days is about the contest. It's just too late, right? It's like late at night, midnight. My brain is not working back then. Look at this. I was able to solve it. So this is, to me, this is what topological sort is. But when I search online, it's like it's a different concept. But it's not topological. It has a name. I forgot what the name is. Maybe we can check discussion and see what other people say about this solution. I just need a name. I forgot the name. Maybe it is topological. I don't know. Come on, what is your name? What is your name? DFS diameter climb up, top down, multi-set. Alright, whatever this is. So graph diameter? I forgot the name of this. Okay, so I thought this method is called topological sort, which after I have read a few online articles, seems to be a misnomer. Anyway, my idea is that we start not from the root, but from the nodes with with only one neighbor, right? And each time such a node is visited, its connection to the neighbor is severed. Right. And thus, each round we will encounter new nodes with only one neighbor. So this guarantees that the path we built is deterministic. Once a node is visited, also as we go to the neighbor, right? We also pass along the current length of the path of the longest path that ends in the current node. If the letter of the current node is different from the neighbor, right? Otherwise, we don't pass anything, and the neighbor has to start afresh. Once a node is visited, we check for all the lengths of previous nodes that have passed to it. Right. We picked the two largest, and they can form a path with the current node be in the connection. Right. Then we pick the largest length as the value passing to the next neighbor. So overall runtime. So each node is visited once, so I think it's ON because each node is visited one time. And we score, I think it's pretty bad. We'll actually see what this one looks like. And of course, DFS on tree. All right, let's see. Classic DFS. I never see the DFS. There's a DFS on this? So I can pick any node with a root, right? And then I'll go all of its children, and then they will tell me the longest that they can form, a single path, right? As long as a single path they can form, okay? And then I can do my trick of just arranging them, including myself, right? And then if it's the same, then this one just give me 0, right? If it's the same, it just gave me 0, and then I can still do it. If it's not the same, then I will return the value. Is that what he's talking about, DFS? Because it is DFS if you think about it. We just, going here and then we keep going down, and we don't go back, right? We don't go back. Let's try it. Maybe we don't even need a adjacency list to think about it. We'll just follow this path. We have a root, and then how do we traverse? We'll go to 1, we'll go to 2. I don't know. I think I still like to turn this into a adjacency list. Let's see. Let's see. DFS. So I still want to do this. Okay. Then what? Then we say def DFS. Well, node. And we return int. Actually, node is also an int. Right. Then we say, what do we say? I'm gonna go to all my paths equals this. Okay, and then for neighbor in adjacency node, if visited. Okay. Zero. If neighbor not in visited, then we'll go DFS neighbor. The path actually dot append this. If it has been visited, now we don't do anything. Okay. Okay. So path dot append, and actually no, if neighbor not in visited, right, and s neighbor is not equal to s node, then we do this. Hold on. If this, maybe I can do this. All right, we say dot append this if they're not the same, else just 0. Okay, so it's the path to handle my neighbor, right? And of course, if not in visited dot append neighbor, and then append dot add. okay, and then a path increment, right? So blah blah blah. Once we're all done, path.sort, and we'll add two zeros here. The path.sort, and then say res equals maximum res paths minus 1 plus paths minus 2 plus 1. All right, we go to all of these, and then we return. And then when the DFS 0, return res. Let's see if this one's right. Huh. A lot of issues. Because I didn't return. What do I return? I return paths minus 1 plus 1. That's what I return. Yep, that is DFS. I mean, I could just say the largest and the second largest, right? I just say P1, P2 equals to 0 and 0. And then simply say if s neighbor not equal to s node, then we say P1 is the largest. P2 is the second largest. So we just say if P equals DFS neighbor, right? And we say if P is larger than P1, P1 equals P. Okay, I'll if P is larger than P2, P2 equals P. Okay, so we don't need to do this, and we don't need to do this, and then this is P1, P2. Okay, P1, P2, and this is P1. Let's try this. Definitely easier, right? Easier than the original solution. We forgot to call a function. Okay. Try this. Huh. It ain't right. How? Minus 1, 0, 1. AAB. Supposed to be 2. Okay, so what's this node? 0. So it's A. 0. And then 1 connects to 0. Which is A. And then 2 is a B. And then we traverse from A, right? And then we want to go to neighbor. Right, it's neighbor, I have A and B. So I go to A. It's not being visited. And then they're not the same. Oh, hold on. I shall always do this, right? Because DFS, I should always do it. But whether I use the return value, that's a different story, right? That's a different story. So I shall always do it. And then, if they're not the same, then I'll update. But this one, yeah, now it fixed, right? It fixed. I don't know why. Neighbors not visited. Yeah, it's not visited. Basically, this one will return 1. I don't understand. Why would this one matter? I mean, I know this is correct to put it here, but why would this one matter? Oh, 0, 1. My bad. I draw it wrong. Yep. Now it makes sense. That makes perfect sense. Yep. So I need to move this one up. All right, try it again. Nope. Nope. All right. I gave up. Let's see what's this correct solution for this. Wide range of. Yeah, the original one is still correct. These are not correct. All right, let's see this one. DFS I return the longest path starting at the node I. DFS on each node I, and for each node I, we iterate on all its children, and all the paths, the two longest can make up the longest path. We update the global result and return the longest path, the result of the DFS. That's exactly what I was doing, right? That's the same idea. What went wrong? Yeah, this one returned the longest path that's starting at this node exactly. That's what I was doing. And I go through the neighbors. And we make sure all the neighbors. And I think he didn't. Oh, he did do this. Yeah, that's my idea too. Oh, this one all right. It's not even visited. Then I do this. And now I visited this. Visit the neighbor, okay? And this will tell me. And now I say, if they're not the same, and I find the maximum, which is if p is larger than this, we do this. Now if it's smaller than equal to p, yeah, but it's larger than p2, then p2 equals p. Okay. And after that, after I go through all the neighbors, I update this and then return the maximum. Where did I go wrong? Isn't that the same as what I'm doing? Let's see. $17. Okay. All right. Then I simply just call it wait, Python has unlargest? What is this? Unlargest. I don't know. I don't know where he got that. I just sorted. Say the logic was correct. It's the way I tried to get to the two largest one was wrong. How? I say if P is larger than P1. I said P1 is the largest one, P2 is the second largest. So if it's larger than this, then we'll update. Oh, I see. Okay, I see. My bad. I know. This is the same problem in the interview of my internship. And I think I kind of stumbled there as well. Can't believe I stumbled here right again. So the thing is, if it's larger than this, P1 equals P and P2 needs to be equal to P1. PS, what PS? Well, there's no PS, come on. Ain't no PS. Huh? Wait, what? Oh. Dummy. P2 equals P and P1. Yeah. Do this. There we go. There we go. Yeah, the problem is the DFS is correct, right? The DFS, but I just realized this can be, as they say, because it's a tree, right? So what I can do, and for this, I don't need to use a set. It can be just like this, right? And then I can just do, because I know who's the parent, right? I know who's the parent. And we just go down, right? We don't go up. So I can just say adjacency parent I dot append I. Right? I don't need any of this. I don't need this. Of course, start from 1. And we don't need this. No need to go visit it. No need this. Yeah. So this is essentially, right? Essentially the same idea as solution 1, but we obviously don't need to use topological sort. A simple DFS suffices. Also, when we build the adjacency list, we can treat graph as a DAG because the problem specifies that the graph is a tree. That is no going backwards. All right, I'm gonna submit this, have a pass, and then call it a day. So we are correct. We are correct. Ooh, 1,000. I gotta record this. That's 100%. Okay. So I understand, right? It's possible to solve all 4 problems. So I think tomorrow I will go look at problem number 3. That one is harder, in my opinion, than this one. All right, that'll be it for today. See you guys tomorrow. Adios.